Good morning, everyone, and thank you for joining me this morning. In the next 45 minutes, I will talk a little bit about some of the Node.js vulnerabilities. Basically, at Checkmarks, I'm the CTO of Checkmarks. At Checkmarks, we do source code analysis to find vulnerabilities in your code. Part of the research is actually we're looking for vulnerabilities or other research papers so we can introduce them into our product. And in this presentation, I would like to share with you some of the interesting aspects of Node.js security, which I hope you will find also as interesting as I did. For those of you who were at my previous presentations, you might know that I'm a great fan of live demos. I really hate video recordings. The downside of live demos is that they might break in real time, so bear with me if something like that happens. So the agenda for today's presentation is as follows. First of all, we will describe a little bit the architecture of Node.js. I believe that since you're sitting in that room, most of you are already familiar with that. But just to make sure we're all on the same page, I will describe a little bit how Node.js works behind the scenes. It will be fairly short. We will describe some of the denial of services that attacks that can be exploited for Node.js. We'll talk a little bit about the cryptography algorithms within Node.js, the JSON part of Node.js. JSON is really fundamental within Node.js, but it brings a whole set of vulnerabilities. We'll be talking about regular expression denial of service, and finally I'll describe traceless routing hijacking, which is a very interesting topic in my mind. So very briefly about Node.js architecture. So Node.js is an event-driven, single-threaded, and non-blocking I/O, which is built on top of Chromium Project's V8 engine. What does it mean, event-driven? So unlike, for example, this is the code. I'm sorry. This is the code. Let me just turn it off. Yeah. Okay, so that's the code that adjusting the image. Okay, so for example, this is the code that finds if a specific file is larger than 1 megabyte in size. So unlike other languages like .NET and Java, where you do find file and if size greater than 1 megabyte, do something. In that case, actually, we're working with callbacks. We call the file system exists function. We send this task for a different thread, and we tell the system, once you find if the file exists, call our callback function, okay? The one that appears right in here. Once you found the file, give me the statistics of that file. Once you get these statistics, call back my callback function. So it's not a linear execution, but rather a lot of callback back and forth. Looking at the architecture, basically there is an event queue. Each event, all the events are queued in a single queue, and it's important that it's a single queue. There is an event loop that grabs each time a single event from the queue and executes it on a single thread, just a single thread. In case the action is an I/O action that takes a lot of time, but not from the CPU, but other devices, the action is sent to a different thread. So for example, if the system wants to read a file, it doesn't happen on the main thread because it will block all other activities. It is sent to a different I/O thread. So this concept means that there is a single thread, which is very sensitive because once this thread is running, nothing else can happen. And this thread basically dispatches requests or I/O-bound requests to other threads, okay? And once these threads complete, they trigger a callback function. They push it into the event queue. So in due time, it will also get executed. So the fact that Node.js is event-driven, single-threaded, it means that on the one hand, the benefit is there is no context switching. A single thread, no context switching, works very, very fast. The CPU doesn't have to wait for an I/O action to complete. It just sends this I/O action to a different thread and then starts doing the next action. So it works well for IO-intensive applications and web apps. It doesn't work well for CPU-intensive applications. So if you have a CPU-intensive application, Node.js doesn't work well. We'll see that in a moment. So let's take a look on this kind of CPU-intensive code. This code looks for the sum of the numbers between 1 to p. For example, if you want to find the sum of the numbers 1 and plus 2 plus 3 plus 4 plus 5, there is a Node.js application which does the following. Obviously, this can improve, but I just want to show something that is CPU intensive. So let me launch that. And let me just zoom in so you can see that. Okay. So if p equals 5, we get 15, and if we do 10, we get 55. Okay, that's easy. Now what we're going to do is the following. I will ask the system, let me just, 100, okay, 100, 1, 2, 3, 1, 2, 3. And I will also show you the task manager over here. Okay, so what I'm going to do, I will send a request to compute the numbers between 1 and 100 million. It is a very CPU-intensive activity. And during that time, Node.js will process no other requests besides the current one. So let me hit enter. Okay. No, let me just another 0 in here. Okay. As you can see, you might be able to see here that Node is taking 25% of my CPUs. I have 4 cores, and CPU runs single-threaded on a single core. So it basically takes the entire 25% that it is allowed to take. Let me rerun that. Okay. And during that time, another user wants to count the summary between 1 and 100, let's say. But the other user doesn't get, no, I talked too slow. Okay? So the user doesn't get any response until the first thread finishes. Okay, so one user wanted to count the number between 1 and 100 million. It takes a lot of time. During that time, no other user is able to get any other response from the server. This shows you how easily Node.js is vulnerable to denial of service. Okay, assuming that one user is able to do a CPU-intensive action on that server, no other users are able to get any response from that server. Make sense? Okay. Now, unlike other platforms, .NET, who is hosted on IIS or in Java with Apache Tomcat, Node.js doesn't have any running web server. The web server is Node.js itself. When you write your Node.js application, you are responsible of handling all the requests, get and post, getting the data and combining it together. There is no web server who manages that. And all that happens within the very same thread of your application. As we said, a single-threaded application. So there is no real separation between the web servicing part and the logical part, all run in the same thread. Now, obviously, there are third-party components which do that job for you, combining requests, get, and post. But still, conceptually, they all run within the same thread as yours. So if you want to write a web application, you don't only concentrate on your business logic, but rather you have to manage all the heavy lifting of getting information from the server. This is a kind of an example where you tell the system to start listening on port 3000, and you create a server. Each time you get a data packet, you have to combine it with the previous packet. So there is a lot of work being done within your thread. Now let's see how it is related. Once we get this architecture, let me show you this example. What's the problem with the following code in here? This is a real code from a commercial application. What might be the problem in that code? MD5 is? Okay, that's one. All right. So math random is really weak. Okay, it is considered the default random within Node.js is considered as fairly weak. So in that case, whenever a new user registered to the system, his password, or her password, is computed based on the math random, then it's being hashed using MD5, and that would be the default password of that user. So as I said, the V8's PRNG pseudo-random number generator is known to be weak. Actually, there is a research from a Maty client that the Maty client wrote, I think, in 2009, how to break PRNG. Google has somewhat improved that algorithm, but still the very same structure remains. Whenever you start having some random numbers, first of all, you get a seed, and then the seed is used to create a private data member called state, actually two data members, state 0 and state 1. And then whenever you ask for the next random number, two things happen. First of all, you derive the first random number from the state, and then you compute the next state based on the previous one. Okay, so you get the seed. The seed is used to compute the first state variables. These variables are used to compute random 0 and state 1. State 1 is used to compute random 1 and state 2. So that's how you get the chain of random numbers. So as we said, PRNG is weak. It means that we were able to show that given 3 random, pseudo-random numbers, we're able to infer what was the state variable used to compute the third value. And what does it mean once we get state 3? What can we do from here?
Predict the random numbers.
Exactly, we can predict the future numbers. Probably we can also know what were the previous random numbers, maybe from other users. But for now, we can predict the future. The problem is that first we need to reverse the MD5 numbers. Okay, so there is a random number. Random is a number between 0 to 1, including 0, not including 1. But then we run MD5 on top of that number. We need to break MD5. How do you suggest we do that?
Dictionary attack.
A dictionary attack? But in that case, it's not a kind of a dictionary where a user chooses his password. It's random. So, sorry, Uto? Okay, so rainbow table are, for those of you who are not familiar, are huge lists of various values and their MD5 computation. These tables are indexed fairly well. So if you got the MD5, all you have to find is the MD5 entry and go back to the original value. The problem is that all available rainbow tables that I found are focused towards passwords. So usually they were created for alphanumeric values, A through Z, 0 through 9, and up to 8, 9, 10 characters. In that case, the source for MD5 is actually a float number, 0 dot, and then fairly large number, about 15, 16 digits. And I couldn't find any rainbow table that focuses on that. So I had to create such rainbow table, and I'll show you how it can be used. That's the actual source code of the random within V8. So as you can see here, state 0 is used to compute the next state and then to return the actual value. There are some magic numbers in here, like the 18,000 and 36,000, and then there is the 14 bits in here and 18 bits in here. Google changes these values fairly often, and this means that the algorithm used to hack the random needs to be changed accordingly. It's not pretty straightforward, but that's the current version Node.js is using. Okay. So given 3 consecutive random numbers, the values of state 0 and state 1 can be inferred. Hence, all future values can be known in advance. But in web browser, in Chrome, each tab runs in a different process. Different process means that the private data members of random are different between each tab. So the idea is that if you have a tab, a single tab, your application, and you compute random numbers, you can tell what's the next state 0 of your tab, but you can't tell anything about what would be the states of other tabs. Okay? So that's kind of a protection. That's why Google doesn't consider, one of the reasons that Google doesn't consider the fact that their PRNG is weak as a real problem, because it's problem coughing within this specific session, within this specific tab. That being said, in Node.js, all users are running within the same process. They're running within the same process. They share the very same state. This means that one user can get 3 random values, get the state, and then the hacker can know in advance what would be the next random values for other users in using that system. Make sense? Great. So we will demonstrate that. So the steps need to be taken. First of all, a hacker would ask, getting back to the source code from the application that we saw, where we get the random and then we compute MD5. You can see it right here at the right button right. So we will register 3 times as a fake user. We will get the fake passwords, or the real password, the random password. So register user 1, get the password. Register fake user 2, get the password. Register user 3, get the password. Now what would be our next step? Not right away. What we got are 3 consecutive MD5 of random numbers. So what would be our next step? Okay, ask the random table, right. So we'll take the passwords. We'll send them to rainbow table. And we'll ask the rainbow table what's the plain text, so to say, of these values. Okay? So we will get the clear random. Okay, so we've got password 1, we'll get the clear random, password 2, clear random, and then the third one. Having these 3 randoms, we will send that to our magic cloud service, which will get us the future password of the user. So let's see how it's going. Now, as I said at the beginning, it is a live demo, and each step takes about 30 seconds, 45 seconds, which is kind of an eternity in terms of the presentation. So please bear with me. So let me zoom out a bit. Okay, so as you see, it's a very secure site. There's a lock, so you're all safe. Okay. So let's register as fake user 1 and fake user 1 password. Okay, so that's the MD5. I'll copy that to Notepad so you can all see that. So that's the first MD5 that we got. Let's register as fake user 2 to get the next password, which we got in here, and then the third password. Okay, we got that. Okay, so we've got 3 MD5 of random passwords. Now let's get to our hacking portal, and here we'll type the MD5 that we got. The actual rainbow table is hosted on Amazon on one of our servers. It's roughly 200 gigabytes in size. That's why it's not hosted on my laptop. And it's not very well indexed. That's why it takes about 30 seconds to get the clear value of that number. It was a bit tricky to get this rainbow table because if you look at the code that we got from Google, basically you get an unsigned int, which is fairly large, up to 4 billion. And then it is divided by max int to get values between 0 to 1. Okay? So you get a uint, and you divide it by max int to get a fairly small number. Now, different platforms give different results. For example, .NET is limited to the last to 14 digits after the dot, where with Node.js it's about 16 digits. So if we compute the MD5 through a different platform, we just get different values. So that's the first clear number for the first password. Okay, 3 billion. That would be the. Let's compute the next MD5. Any questions so far? Okay, So we'll wait patiently till it finishes. So. Yeah, good. How to generate secure random with Node? Yeah, there are some there are some modules which do proper random generator. I mean, proper is a bit, they're all pseudo, but some of them are able to get values either from network traffic or from your mouse movement. They try to get some noisy to get the entropy for your random numbers. Okay.
Could you give Stanford crypto JavaScript library that's just quite good quality random, as you said, from the client function?
Okay. Do you have the name of that?
SJCL something like that.
SJCL.
Search for Stanford crypto JavaScript library. It's SJCL. It's on GitHub.
Oh. And we're soon to be.
How long did it take?
I'm sorry?
How long did it take?
About 24 hours. On an Amazon M3 large, something like that. Because we have to compute it for, basically we have to go through I from 1 to 4 billion, and for each one of them divided by maxint and compute the MD5. I'm sorry? Yeah, I thought it would be faster, but well, I didn't do the hard math myself, so it's okay. Okay, good. So we got the third number. So we have here the three clear text versions of the random. And now we will run the raking random part. Once again, it also should take about hopefully less than a minute. And what we expect to get as a result is first the next random number, clear text number, followed by the hopefully next password generated by the system. While this is running, let me load that screen through Internet Explorer just to show that it's really server-side, so nothing is on the client. So other clients from other places working with the same. Okay, still crunching some numbers. Now the next question usually I'm being asked is how the hacker knows the username of the user. So we'll know the next password, but we don't have access to the username. And that's a valid question. So in case these are forums, you can look for other users in these forums, or if the username is kind of a consecutive number, you can get that from there. It really depends on how and what system you're using, but I wanted to focus on the password part. So the system tells us that the next password to be generated is the following, okay? Well, it seems a bit short, I guess, I'm sorry. Would be the following, okay? So it will be the CE6 ended by D62. So let's, crossing fingers, real user 1, and then email whatever. Let's register. And the password is, okay, you can see it in here, CE6 ended by D60, yeah, ended by D62. Let me, okay, so let me just zoom in a bit so you can see that in here, okay? So you see the password in here. It's not any large, never mind. Okay. Next topic is a little bit about SQL injection in Node.js. That's really interesting. MongoDB, unlike other databases, is considered as a NoSQL database. Okay, so there are no tables and records. Rather, there are collections and documents, and all the information is stored as a JSON. The next part I will show you is part of a research done by WebSecurify about a year ago, which is really interesting. The idea behind documents is that each record or each document can be structured differently. For example, the first document here has an item field and a quantity field, where the second object has the data field name and the second field size. So you can store both of them at the very same collection, different different data members. In order to retrieve information, you can use the find method to get all the information. Or you can express your query in a JSON format. For example, I want to find all the elements where their quantity is 15. Now, an interesting point is that the 15 as a value can be replaced with another JSON object which actually contains an operator. For example, find all the products that their quantity is greater than 25. Okay, so instead of a concrete value, we can actually push JSON object. Okay, within the code, JSON can be translated like that. So we have an object var obj, and then obj.quantity equals to 15. Database product find of elements with these qualifiers. So this is a classical SQL injection. Okay, select star from where, and then we concatenate username and password. And to get it fixed in Node.js, all you have to do is to use the prepared statement. Name request query, get the username from the request, and then get the password from the request, and just push in the name into the name and the password to the correct field. Okay, make sense? Wrong. That's not how it should be done. Okay? Let's look how the system basically, if you've seen here, we took the query string from the URL and we converted it to an object name. And Node.js actually does very interesting stuff when it parses the URL, and we will take advantage of that. So if, for example, we write at the URL a equals b, it will create an object, query string, with the field a, and its value is b. If we convert it to JSON, we will get this structure. If you write a equals b and then c equals to d, we get the same object, data member a with the value b, and then data member c with the value of d, and that would be the JSON structure. We're writing a equals b, c equals d, and then again a equals z, okay, z. We actually get an array, okay? A is an array that contains two elements, b and z, and then c is just a data member with d, and the JSON will look as follows. Okay, a, and then an array of values. If we put a numeric indexer, a at the 5th location, we will get the very same array with a single value of b. Okay, and the JSON will be translated as follows. However, if we use a string as an indexer, as you can see here, we use the letter S as the indexer. Instead of actually having it set into an array, it will create a sub object. So obj.a.s equals to b. And the JSON part is interesting. You get that a equals to another JSON object with the key s and the value of b. Okay, so it actually creates a sub-element, sub-JSON element. Now, I hope it rings a bell that the previous slide, we actually showed that we can use the greater than operator. So we can take advantage of that in a short while. So let's actually see that in action. Okay. So this is a system. If I don't know username and password, A, B, C, D, E, F, well, sorry, that's not correct. And then if we use admin, we're able to log in. We can do the same from the query string. So if I try to log in as admin, that's perfectly fine. But if I try to log in with a different username and password, I'm unable to log in. Since, let's assume that we don't know any the valid credentials, we can use at the user to use the indexer of greater than. So we'll use the greater than operator, greater than a, and then the password greater than a. Okay? In that case, the system will look for an entry that, a record or a document that matches greater than a. And I was able to log in as an admin. Okay? And then we can iterate through the different users. For example, then we can use the password greater than you, and we see another user. So we can actually iterate through all the users in the system, or to log in as the admin without knowing a valid username and password. Any questions? Yeah. I'm sorry? So I'm not sure who found the vulnerability, but it is very well documented at the WebSecurify blog. Okay, I'm not sure if they have found it, but it's an amazing write-up. I really recommend you read that. It's called WebSecurify blog. Really excellent. Now, one of the proposed solutions is to use the following. Okay, db.user find a user given the username, and then retrieve the password, and then compare the password to the password that is stored in the database. Does it solve the problem? Why not? Someone said no. Why not? I inject the username, then we get, let's say, admin. Then we get the password, and we compare it with whatever the user typed at the text box. So what's the problem in here? Okay. So the thing is that we can still inject something through the username field. Looking through the various operators that can be injected, like greater than and less than, one of the operators is regex. So we can actually look for username that the name matches a specific regex. And then we can use that to do what is called regular expression denial of service, to provide a regular expression statement, which is so difficult for the server side to compute, which will consume, well, all the CPUs during that time. So that's would be an example. Let me just copy paste it. PowerPoint didn't want to create a real link from that, so I have to use copy paste. Yeah, so that I don't really know. Okay, adjusting image is good. Okay, so I will put that into here. Let me just paste. Chrome doesn't like it, okay? Now, once I hit enter, you will see here that the MongoDB service, the service who manages this request, will use 25% of the CPU, a full core, for about 3 to 4 seconds. Okay, so let's see. So let me hit enter. And you can see it in here. Okay, so MongoDB takes a few seconds to validate the username that they just typed. So during that time, probably no other users can get service from the MongoDB. They actually can, so after 5 requests, it stops. But basically during these 5 seconds, no other users could have gotten any response from the MongoDB service. Okay? And that's probably every Node.js application is vulnerable to that part. Okay, any request that you send to the database where the values come from the user might be vulnerable to that. Probably the best solution would be to use character whitelisting. Okay, so there is no reason to use square brackets as an input for a username. And there are some modules with Node.js that can be used to automatically validate any input for a specific format. But unless you use any of these, by default, your Node.js application is vulnerable. Any questions so far? Okay. Now, recapping, if you recall, the traditional Node.js doesn't use any traditional web server. This means that your code is running at the same process, at the same thread as the web server. This means that problems in your code can affect the web server itself. Now, what I plan to present right now is, well, I wasn't sure if I will present it or not. The thing is that we all know that eval is evil. That's fine. I do want to show something additional that can be done with the eval. We all know there is a problem with that. I just want to open your mind to a different attack vector, which I really found it interesting. What I plan to show now was taken from that research, the analysis of Node.js platform. So in most web servers, each request spawns a new child. With Node.js, it's a single-threaded. This means that a modification to the system that are done by one user will affect all other users immediately. So eval evaluates a string. In .NET and Java, eval cannot control, for example, in .NET, eval cannot control the IIS. Okay, the IIS is a different process, and the .NET application cannot control the web server. With Node.js, Node can control the web server. So we will show the demonstration will be shown on Express.js. Express.js is a module that provides web servicing to Node.js. This is, for example, if we want to add a page or a service called add to our application, we create what is called a routing. Okay? So that's a routing. For example, if we want to access the server at the add page, then we add a new route called add, together with the code right here at the bottom. So this service does just adds two numbers. For example, it adds the number 3 to the number 8, and we get the number 11. It does it really badly by using eval. So evaling the first data member with the second data member and combining the two. But some really interesting stuff can be done in here. So the actual routing is done, but what they call the stack. So there is a routing stack, which contains all the available pages, and each one points to a specific function. So we see here that adds point to function 1, remove goes to function 2. There are some parameters for RESTful API, so we get the ID used for the page. And we can use some regular expression. We won't focus on that part in here. But I want to focus on the fact that we have a route to the add method. And our system can access this stack. So let me click in here. And we get the full list of all the routing used by our system. So we've got an eval. Thanks. We've got an eval. And the eval code that we pushed in here is to get the full stack of the routing of our system. So that's one. So the stack is accessible in runtime, both to read and to write. So we will replace the existing routing with a new one. And this will affect all users connecting to the system. And it looks very weird because, well, I'll show you exactly why. So basically, we've got the add. The first command that we will send is to actually remove that routing from the system. And we will add a different routing with the very same name add, but it will point to a different function, function 5. So any future users going to the add page will actually see something different than one that was what they expected to see. Okay? So, no, well, it calls to a different function on the same server. Your function can do whatever you want. Yeah, I guess. So what you're going to do are in 2 steps. First of all, we're going to go to the route stack, and we will remove, in that case, the third element, which is our add page. And then we will immediately afterwards push another add, which will just take the 2 values and multiply the 2 instead of summing the 2. Okay? So let me run this code in here. So 3 plus 8 equals to 11. Okay? And 3 plus 9 equals to 12. So everything goes fine. Now we will hit that, which, as you can see here, removes the third element and adds another one. Everything looks fine. And then now a user wants to know how much is 3 plus 8, and he gets 24. Okay? So now any user connecting to the system will get will actually use our multiplication service instead of our adding services. So the funny part is that it seems like a bug. So you will approach the vendor and say, well, I see something going wrong. Looking at your Node.js source code, you see nothing wrong. And if you try to further investigate it, upon a restart of the service, everything just is completely removed. So you have no tracking of what actually happened behind the scenes. This attack lives just in memory. It doesn't store itself on the disk. I think we're towards the end. They were clapping. Any questions?
Sorry, so how to protect against these attacks? Especially the last one.
So first of all, don't use eval. That's pretty straightforward. That's really bad. I just wanted to show what else can be done with that.
And is there a way to enforce not using eval?
Well, you're welcome to come to our booth, I guess, and discuss that.
How about strict mode?
I'm sorry?
How about strict mode?
Trick mode?
How about strict mode?
With Node.js? I'm not familiar with that, so I don't know to answer that. Sorry. Thank you very much.